Okay, good. Could you hear me and see my screen? Uh,
Uh,
yeah.
sure. Okay, yeah.
Okay, we
Louder.
we just started, and I think it's the time for beginning, and it's 9 o'clock at the Thailand, and nice to meet you all. This year actually is the first year of our workshop, Multimedia Object Reality Advancements, Challenges, and Opportunities. And me and Yaxiong and Xueling and Zheng and Zheng and Liang, we are holding this workshop. Actually, we want to have a chance and have an opportunity for all interested persons to join us and to share their new sides and new opinions towards the object reality, right? So today we will have the three invited speakers, Punan from the University of Trento, uh, Professor Lin Yutian from the Wuhan University, and Lu Zhihe from the NUS. And after the three invited talks, we will have the three oral talks from the authors. Right. This is the today's tentative schedule. Okay. And actually, this year our workshop actually received about 10 manuscripts, and only 5 papers are accepted. And yes, here we want to congratulation to all authors and for their great works. Right. Okay, we also have more many reviewers and reviewers from different area, different regions, and they also do a great work to provide us very valuable feedback to the authors and let the authors to improve their papers, improve their writings. So here we also want to thank all reviewers and their efforts to our workshop. And actually, after our workshop, we still have 2 workshops, and which we will be held on ACM Multimedia this year. And these 2 workshops, one is for the UAVs, which is also about retrieval problems to retrieval the ground view to the satellite view, to matching the satellite view to the ground view, and to do something like that. And we also have the second international workshop on deep multimodal generation and retrieval. And which is also will be held on the ACM Multimedia this year. And you are welcome to attend our workshop at Melbourne, Australia this year. Okay, this is all about our workshop and the future workshops, and hope you will enjoy our today's talk. And okay, I will stop my screen sharing and let's welcome the Dr. Punan. Yeah. Thanks. And actually, Punan, he is doing a well job during his PhD at the Leiden University. And after he graduated from the Leiden University, he come to the University of Trento at Italy. And let's welcome Dr. Punan. Yeah. Okay. Let me stop sharing. Uh, Stop sharing. Sorry. Sure. Mm. Post share. Stop share. Okay, good.
Okay, thanks for Zhedong's introduction. Uh, uh, but now I still cannot share my screen.
Maybe you raise issue and I will accept it. Yeah. Let's
Um,
see. How to post sharing, post recording. No, share screen. 1% can
Maybe
share.
you should open the multiple share.
Yes, I just opened a multiple share and you can try it again.
Yeah. No, it's working now.
Ah, thanks.
Okay.
Great. Yeah,
Yeah.
great. We can see your screen.
Okay.
Yeah.
Thanks. Hello, everyone. I'm glad to give this talk at this workshop. Firstly, I would like to thank all the organizers who provide these opportunities. Today, I would like to give a presentation about the lifelong learning.
Sorry, I
Sorry.
can't see your screen. Yeah. Okay. Okay, I can see it right now. Yeah, sorry.
Okay.
It's,
Um,
it's
so it work now? Works now?
Could you please full screen?
I can see the pronounce slides. It works. And sharing, maybe it's due to the network. Could you check it? I
Okay,
can
just
see
wait a
the
Uh,
minute.
screen of from
okay.
actually.
Okay.
Just because it's working. Okay. Yeah,
Yes.
and I see the screen. But it's the full screen. I think
Yeah. The first page. Full
oh
screen.
yeah.
Okay. Let me stop here. Okay.
Maybe share again. Actually, I
Share
can see the
again.
full screen, and
Yeah.
yeah, is it good now? Sharing.
Yes.
I think I need to wait a minute. So yeah. I think it's because they
Okay.
Maybe due to the network issue, it may take some times to work.
yeah.
Yeah.
Okay.
Um
Um, can you see now? Or
Sharing, you may try close the video and see whether the network will work. Uh,
just just wait a minute. Let me. Sorry.
um,
Zedong, can you see my screen now?
yeah, I think it works for me, but maybe it will not work for the Thailand.
Okay.
Yeah, due to
Okay.
the network and about the
Something.
battery.
Okay. Okay.
Maybe we will wait for sharing a little bit.
Um,
Yeah.
okay.
Actually, we also record our workshop, and later we will
Mm,
upload to several like YouTube and other video website, and I hope it will share with more peoples. Yeah. So
yeah. It will be nice. Yeah.
yeah. Let me see.
So maybe we can check if the first problem is from my side. Maybe we can let the next speaker to share their screen and see
Um,
whether.
no, I think not. I can see your screen
Okay.
and it works.
Okay.
So I think it's about Thailand and okay, sharing is coming.
Yeah, hi.
Hi.
Can you hear me? Yeah, okay. Sorry about any inconvenience. We are good to go. Yeah.
Okay. Let's start it again, and we thank for the Dr. Pooh to come and share his insight. Yeah, let's go.
Hi everyone. Today I'm going to give a presentation about lifelong personal identification. Basically, personal identification is to search a certain people across the disjoint camera view. A general pipeline to design a personal identification system has almost 5 steps. Firstly, we need to collect the raw data, which could be image or the frame in a surveillance video. Then, because personal identification is aimed at searching persons, so we need to detect the person and generate a bounding box to crop the person images from the original frame. But recently, these technology are very mutual. After that, we need to annotate this data to train ReID models. Finally, the model can be deployed at the target places such as the crossroad, shopping mall, and university campus. Given a person of interest, namely query, and a gallery set, we calculated the query to gallery similarity by the ready model. We regard the most similar image in the gallery as a true match. But we should note that most person-ready papers are focusing on improving the model's performance on the stationary dataset. The stationary setting here means all the training data should be pre-collected and need to huge storage space and computational resource as well. In short, the stationary setting are not very practical. In contrast, non-stationary setting is more practical but challenging because the training data could be incrementally arrived. For example, the data might be instance stream data or the dataset stream data. Let's see, at a crossroad in a city, there will be a huge volume of video stream captured by hundreds of cameras day and night. We cannot store all of the historical data to train a ready model due to the limited storage space. Thus, we turn to consider whether we can incrementally train a ready model with only the current data in hand, but achieve a generalized model that is effective in all domains. To investigate the above-mentioned problem, in our work, we first proposed a lifelong ready task. It is a domain incremental setting. Each domain has a distinct characteristic, including identity, camera pose, illumination, background, and dressing style. The target of this task is to continually train a ready model across multiple source domain. And the final trained model need to not only perform well on all scene domains without forgetting, but also generalize well on the unseen domains. In each training step, the model training can only access to the current domain data. A simple solution for lifelong ready is directly fine-tune the model with the new data. However, as shown in the middle figure, the method suffers from significant forgetting issue on the scene domains. On the other hand, the model meets more dataset doesn't mean better generalized ability. As shown in the right figure, interestingly, when the model meets Duke dataset, the generalization ability decreases a lot here. Consider a fact that human can accumulate knowledge and acquire stronger capability by learning more cases. So we try to endure the model with such ability and try to find a possible solution from the perspective of cognitive science. From the recent discovery of the cognitive science, one possible reason why human can perform complex cognitive process well is that our brain relies on two relatively independent mechanisms. One is knowledge operation, another one is knowledge representation. In this case, when people see a person images, our brain will recall the similar person image in our memory. Here, the recall is a kind of knowledge operation. And the person image in our memory is the knowledge representation. After seeing a new person, our brain updates our memory, which is another knowledge operation. These two mechanisms are relatively independent, which enable our memory to be stable and to firmly accumulate learned knowledge. So we aim to inject these two mechanisms in the lifelong ready model. Motivated by this, we proposed an adaptive knowledge accumulation framework to achieve this goal. We parameterize the knowledge representation and the knowledge operation by graph convolutional network. Firstly, we establish two different knowledge graphs for knowledge representation. One is ISG, another one is AKG. ISG is responsible for extract knowledge among current batch instance, and the AKG serves as a learnable memory buffer it is optimized across all domains. During training, we perform graph convolution to enable these two graphs to perform cross-graph communication. That is a knowledge operation. And the whole framework is optimized by stability competition objective. The vertex in this ISG is obtained by the instance in the current branch. AKG is a learnable buffer to accumulate knowledge from the different domain. At the beginning, the vertex of AKG is randomly initialized. Here, we consider these two graphs include two types of knowledge. So we use a different parameter to model the affinity relationship among their vertex. In contrast, we design non-parameter affinity for the cross-graph communication to achieve knowledge operation. This has two benefits. From the view of ISG, it can retrieve the informative knowledge from the memory and thus enrich the feature representation of each batch sample and obtain better generalization ability. On the other hand, from the AKG perspective, this operation can update the memory with the current batch knowledge. This can continually accumulate generalized knowledge. Overall, this graph framework is optimized by the stability plus plasticity competition loss. The stability loss constrain the AKG changing and keep the knowledge representation in AKG stable. The plasticity loss enhance the generalizability of the fused representation, benefit from the AKG. This competition works like a bottleneck, which imposes the knowledge representation stored in AKG to be compacted and representative, as well as able to generate a generalizable feature. Furthermore, as re-ID is a retrieval task, it is important to enforce the model learn discriminatory representation based on the ranking relationship. So we proposed a differentiable ranking consistency distillation approach to enforce the model to explicitly consider the knowledge of ranking relation between samples during the distillation process. In short, the ranking sort should be consistent between the current model and the previous model. As we all know, Spearman distance can be used to calculate the difference between two ranking orders. However, this leads to two problems. One is that it ignores the importance of the different position in a ranking list. And another one is that it is the discontinuous process, so we cannot directly use it to gradient-based optimization in the deep learning. So to solve these problems, we proposed adaptive ranking position weight and a differentiable ranking list. The weights are adaptively learned at each domain training. We use a hyperbolic function to approximate indicator function, which lead our RCD to be differentiable. We show the weight learned during training. We can find that with the training process, the model turned to assign higher weight to the hard sample during training. As a result, our RCD learns adaptive weighting manner that always assign higher weight to the hard sample during training. We also compile our adaptive weighting to different methods and find that our method achieved the best result. In addition, the reinitialization before each domain training is important, as the model is not familiar with the current domain, and all easy and hard samples are both important. As the training processes, the model needed to pay more attention on the hard samples. Also, we evaluate the effectiveness of our proposed function. We found that simply use GCN here fails to achieve improvement, and found that all the loss functions are important to improvement. We compare our method with the SOTA methods, showing that our method obtained the best result on seen domains and also the unseen domain. This demonstrates our method achieved good ability on both generalization and the anti-forgetting performance. In summary, we proposed a new practical task called lifelong ready person ratification, which help us to explore the scalability of the ReID models. We propose a knowledge representation and operation graph-based approach, which enable the model achieve better balance between the good generalization and anti-forgetting ability. Also, we proposed a ranking knowledge distillation approach, which is tailor-made for the ReID task. Here, I have some takeaway idea for future lifelong learning research. One is about the unlearning or decremental learning. Let's say we have an incremental training ready model, but one of the training domain include sensitive things or sensitive persons. Thus, we need to delete or erase the sensitive information and keep the model's performance on the other domains, which could be a good research direction for the future ready. Finally, I would like to thank all my collaborators and supervisors. Thanks for your attention. Welcome any comments and questions.
Thanks. Thanks, Dr. Pru. And actually, yes, I will have two questions. The first question,
please.
yes, do you, I mean, the graph network, usually they have a similar opportunity as the re-ranking. So will your method still could further improve after you using re-ranking?
Yes, of course. Because
I see.
re-ranking process is like the post-processing method. If we or the proposed graph network work in an online learning way. So I think we can combine those two process.
Okay. Okay. Because usually we think maybe the graph network can do the clustering and the
Yeah.
ranking also do something like the clustering. So I just wonder whether they have the same opportunity and the same function, so the improve will not be so high. Okay, this is my first question. And the second question, have you ever considered using other like the distill function, for example, the KL divergence? Why you choose the Spearman
Spearman distance.
yeah, Spearman distance. Why you choose it? Have you ever considered using like the KL divergence or some different functions? Right.
Yes, actually, in my papers, we also choose the three different type of distance metric for comparing to list. But I think KL divergence is a nice metric for multiple tasks. But considering the ReID task is a kind of retrieval task, so the ranking result is more important or more suitable for the ReID task. So I think KL divergence didn't consider the ranking information here. It consider a distribution or the other kind of distance. So I
Yeah.
think the ranking loss is better than the KL divergence loss here.
Yeah, good. Yeah. Sorry, have the audience, do you have any questions? You can raise your hand or write it in the chat. Yeah.
Yeah, okay, thank you, Dr. Put. Any question from the live audience?
Yes, please. Can you speak aloud? Sorry.
Yeah, we can hear you loud and clear.
Okay, no problem.
So I think
Mm, yeah, maybe I raise another question. And yeah, so the data set, which data set do you use? Still is the market or Duke?
Yes, for the source domain, we use 5 popular datasets, including Duke, Market, and SYSU, and also uh, the SU Market and CUHK. Yeah, CUHK.
Okay.
Zeros.
So the final result, maybe we come back and see your final result. So the
Yeah.
final result is still evaluate on 5 datasets, or okay, I see. To
Yes,
see
here.
whether yeah.
Yeah, we have two evaluation protocol. Firstly, we need to evaluate the model, the anti-forgetting performance of our model. And
Yeah.
another hand, we need to evaluating the generalization ability. So for the anti-forgetting evaluation, we use the original test set for its corresponding data set to evaluate the performance. And for the generalization ability, we reorganize the other 7 different data sets. Maybe it's Vapor and Pride and other 7 data sets served as the generalization domain. We use that 7 data sets to evaluate the generalization ability.
Okay, the protocol, the balance and the imbalance means the sampling rate or something like that.
Yeah. In the balance setting, we all the domains for each domain we sample 500% to build the training set. But for the imbalance case, we just use the original data set.
Okay. Yeah, I just one of my idea, whether you consider using like the stable diffusion XL to generate the samples for training. Maybe it can be better, or I'm not sure.
Yes, exactly. Because in lifelong learning community, we will have a kind of approach related to the data replay. This kind of technology often work better than the data-free methods. But
Oh,
our lifelong personality is a kind of data-free lifelong learning method. So if we can use some method to generate a generate images from previous domain or something like that, I believe the performance will better.
yeah, sure. Yeah, it's nice. Let me see. Uh, yeah. Any audience have their, I mean, have other questions? You are free to raise your hand and ask the doctor who. Yeah. Um. Let me see. Oh, okay, good. So, thanks for the Dr. Pooh, and we will have the second talk, which is from the Professor Lin, and she will prepare his slides. Yeah, thanks. Thanks.
Thank you.
Yeah.
Oh, okay. So thank you, Dr. Pru, and thank you, Professor Zheng. And we are going to switch the computer for the next speaker. Yeah.
Actually, the Professor Lin is also graduate from the UTS, the University of Technology Sydney, And after she graduation, she come to the university, Wuhan University, and now she is a research associate professor, right? And today she will talk about her recent work on sorry, few short reality, I think. Let me check it.
But just wait a minute, let us share the screen, okay?
Yeah. Yes. And Professor Lin actually do lots of work on person ready, and today she will talk about the future, the privacy, sensing related works, sensing related issues, which have not been totally solved in person ready, and yeah. Okay, let's welcome the Professor Lin. Yeah. Okay, okay, I can see the screen. Yeah.
Okay, so can you hear me?
Yeah, but I see the mode is not correctly. I see the presentation mode, not the yeah.
Let's see. How about this mode?
Yes, it is correct. It works now. Let's
okay.
Okay, let's welcome the Professor Lin. Yeah, thanks.
So, good morning. I'm Yutian from Wuhan University. So, it's a great honor for me to participate in the multimedia object ready workshop, and I sincerely thank Zhedong for the invitation. So, the main topic of my talk is privacy protected person identification. And person ID is a well-known task, and the goal of person ID is to find the specific person from images captured from non-overlapping cameras in diverse locations. And most existing person ID researches rely heavily on real pedestrian images collected under surveillance cameras as training samples. So some commonly used public datasets like market or MSMT17 are all collected from surveillance cameras. So, however, the individuals are sometimes they are often unaware and unauthorized to have their personal images used, and this will expose personal private information and further incur security issues. For example, the dataset the Duke dataset has been withdrawn because of the privacy issues, and the images of the red dataset MSMT17 are asked not to be shown in any form of publication. So the above phenomena make us think that can we achieve privacy protected ready? So note that as shown in the figure, most existing ready method include supervised or unsupervised domain adaptation or unsupervised ready methods. They all face the problem of privacy leakage since the ready model is trained with target real person images. So to evaluate the privacy issue in the ready task, we propose to learn a discriminative model without access to the person appearance of the target dataset. So here we propose a new setting of ready that we don't want to access any real person appearance during training. So under the privacy protected person ready setting, the person appearance from the target dataset is unseen. So therefore, we turn to the virtual samples generated by the game engine. And here we present 4 datasets that collected from game engine. They all have diverse person identities, and some of them are collected and some of them collect person images in different illumination, viewpoints, backgrounds, and weather. So with these virtual samples during training, the service provider is only accessible to the virtual images, and the procedure of evaluation can be done in the black box. So in this way, we can achieve the goal of privacy protected ready. Okay, so then the main challenge of privacy protected ready lies in the absence of target images and the huge domain gap between the virtual and real images. So to bridge the gap between the virtual and the real domain, we propose to make use of the privacy relevant content from the real person images. So here we found 3 types of privacy relevant information from the real target domain. We can see from the figure, the 3 are the content information, including background and the pose of the real person. And the second one is the imaging information, including the resolution and the illumination environment. And the third type is the description information, includes some semantic distribution, includes some semantic description, such as some attribute of the person. Okay. So by considering the content information, such as background and the pose, generated virtual samples can have more realistic features. And by considering the imaging information, such as resolution and illumination, the image style can be transferred to mimic the real domain. And by considering semantic information, such as the clothes of the pedestrian, the generated virtual samples are forced to have the same semantic description as the real target. So here is the overall training pipeline of our proposed method. And the pipeline consists 3 modules. So since we have just discussed the target real image provides 3 kinds of privacy irrelevant information. And so we take advantage of the content, imaging, and the description information, and conduct the image translation, image rendering, and image sampling, respectively. So in the finally, we can obtain images as shown in the figure. We can obtain images that have the similar distribution of the real target images. So we can train a better ready model without the real person appearance. Okay, so in the following, I will introduce the 3 modules. Okay, this is the first module, the image fusion module. So in this module, we want to make use of the content information, include the background and pose to generate virtual samples of the virtual appearance and the real background and the real pose. Okay. So how can we control multiple factors input to generate images toward the target distribution? So without other factors, a practicable method is to use a VAE model. However, in our task, there are multiple factors that need to be disentangled in the latent space, where one of the factors is a foreground character from the source domain, and the rest are from the target domain. So as shown in the figure, we propose a multi-factor variational generation network. So this network, the MWT network, takes the foreground character, the background, and the pose as input into the encoders, respectively, to obtain their low-dimensional features. And before fusing with the character's identity code, the MWT network concatenates the codes related to the target domain, the joint coding information, and to model the intermediate code that would describe multiple factors and keep the information not lost. The bottleneck will adopt auto-regressively modeled groups to construct the joint latent variable representation. And in the end, we use the to optimize the whole network. So here are the samples images generated by the multi-factor variational generation network. So given the pose and the background from the target domain, virtual samples with various real poses and backgrounds are generated. Okay, so we can see from the generated images, the generated one are with the virtual image, the virtual pedestrian appearance, but with the real background and real pose. So this generated virtual samples could be more can be more close to the real ones during training. Okay, so then let's move to the second module. The second module is the image rendering module. Okay, so here are some samples from market dataset. We can see from the left set images that for each identity, there are images of diverse illumination environments. And from the right side images, we can observe that the foreground resolution are also very different. So here we want to adjust the illumination and foreground resolution of the generated virtual images according to the target real images. Okay, so first, for the illumination distribution adjustment, each image is first converted into the HSV format, and the V channel is extracted. We calculate the average value of the V channel as the illumination value of the image. And then the illumination value of the images from both the virtual source and the target domain is calculated. In practice, we adjust the illumination distribution of the source domain by multiplying the same coefficient for each image to make the two distributions have a similar peak distribution. Okay, so for the foreground resolution distribution adjustment, the mask map of the person in each image is obtained. Then the number of pixels occupied by the characters in the mask is divided by the number of pixels in the whole image to get the percentage. So to adjust the foreground resolution distribution of the source domain, we scale the foreground of the source domain to have a similar percentage distribution to the target domain. So here are sample images generated by the image rendering module. We can see that image with the adjustment of foreground resolution and illumination are more have more diverse appearance and can be more close to the target real ones. Okay, so let's move to the third module. The third module is the image sampling module. So the figure below shows the distribution of attributes of the top close color and the bottom close color in 3 datasets. We can see that among the 3 datasets, the market, Duke, and person X, where person X is a virtual dataset. We can see that among the 3 datasets, their attribute distributions are totally different. For example, in Duke, nearly all people are wearing black top clothes, and there is nearly no person wear green clothes. However, in person X, there are many people wear green clothes. So here we want to adjust the attribute distribution to make the generated virtual images have a similar attribute distribution with the real target. So we use the sampling strategies to resample the images with a similar close distribution. So here are the comparison of top and bottom closing color front attribute distribution before and after adjustment. So we can say after adjustment, the adjusted person X, the yellow one, they have a similar attribute distribution of the real market dataset. All right. So with the 3 modules we just introduced, we have with the 3 modules, we can generate virtual images that are very similar to the target real one. So we use the newly generated virtual samples to conduct our experiment. We can say that the baseline is only about is only about for the baseline is a person X sub 1, which has 46.1, which has 34.8 then rank 1, and ours improve the performance by 30 points. Okay. And here are some application studies of the method. We can say that the proposed 3 models, they all contribute to the baseline. And the images below shows the distribution of the foreground resolution and the distribution of the illumination and the histogram of the illumination distribution. So we can say that after the adjustment, the distribution of the virtual images shown in light blue gets closer to the real condition for both resolution of foreground and illumination. Okay, so in conclusion, we find that the privacy is ground, just like the 3 laws of robotics. The first law is the robotics could not harm person. So we think all computer vision techniques, they can have very good performance, but they should keep the privacy first. They keep privacy and couldn't harm person. So in this work, we propose a new setting, privacy protected reality. So in this setting, we do not access to any person appearance information, or we just access to the real background and real pose and some real illumination or resolution or attribute information. Okay, so that's about the privacy protected ready. And now this is a generation, it's a generative AI age. So everyone can generate an image in 1 minute, and privacy is being even more important. And there are all kinds of person-centric privacy issues like deepfake, identity fraud, and image manipulation. So in the next part, I want to introduce the new work of our research group. We propose a new data set about the deepfake attack and defense. So even though the field of deepfake detection has existed for quite a while as an important research topic towards the recent responsible development of AI systems, the recent popularity and fast advancement of generative AI have encouraged us to rethink and revisit the challenge in this new age. So if we think about the overall research pipeline for the deepfake detection, there are about 3 components. So in the upstream form, there are core generative technologies. And the middle part involves deepfake dataset and benchmarks, and they are developed for the downstream detection tasks in various granularities using different generative sources. And on the downstream side are the detection methods, also corresponding to the granularities and evaluation practicals from the datasets and benchmarks. So our work resides in the middle part of the pipeline as a new deepfake detection and benchmark that serves 2 purposes. So on one hand, we hope to bring new recent generative AI technologies to these datasets, as some of these new tactics bring new challenges that hadn't been addressed in the existing dataset. And on the other hand, we seek to introduce a more unified formulation and evaluation protocol for detection in different granularities and also less biased, closer to the real-world scenario. So in terms of the new techniques, existing datasets mainly include two classic forgery operations, which are face swiping and attribute editing. However, we found in our benchmark experiments that due to these two operations have highly consistent and repetitive patterns for editing. And in other words, because they always added some fixed regions, either the whole face or attributes like eyes and nose. So they to introduce the relation for the downstream detection modules to always recognize those certain regions, and thus leading to a high false alarm rate. So to address this, we noticed that recent generative AI technologies have the imprinting operation be flexibly applied in random patterns that helps to mitigate the correlations. And it also reveals a new type of risks to alter some fine-grained low-level visual information without altering the image semantics. So in terms of the evaluation, we note that the existing deepfake detection community works in a relatively independent manner, meaning that researchers develop methods for specific scenarios, such as the whole image classification or regional fake detection. So our data set, even though mainly constructed with regional forgery operations, can be applied both in the whole image or regional fake detection setups. In the training and testing speed, unlike existing data, we mix both real and edited images to enable both image level classification and regional mask prediction at the same time. So overall speaking, our dataset contains in total 300,000 edited images. We integrate 3 different generative operations with editing areas in different granularities, which includes face imprinting and attribute editing. And all the editing operations are achieved by SOTA and representative GAN and diffusion models. We also ensure the visual quality of data by human study and large language model evaluations. So through data, we hope to encourage the responsible usage and development of those generated data. So thank you.
Yeah, okay. Thanks a lot, Professor Lin. And could you go back to the last slide? Just some question. So have the students or any person to manually check whether the edited imagery is good or not? Yeah. Do you have any, the students or
Yeah.
annotators to check the quality of the edited image? Because as far as I know, some editing is quite obvious, right? So whether it is still cheating for to the human, yeah.
Yeah, it's yeah. we have students that check the edited images, and in most of the times, even human can't find the edited areas.
Okay, I see. So whether the data source is from where? I mean, the images is collected from the Coco or Flickr or
Uh, yeah. The images are from yeah. I think we have many resources, and sorry we didn't list it here, but there are many resources.
Okay, I see. So the final task is to do the editing mask prediction, right? The final result is to protect the mask or just to recognize whether it is edited or not.
First we want to we want to do the classification in the image level to find if it's edited or not. And second, we want to do the region detection. We want to find the exact edited regions, the specific regions that have been edited.
Okay, have you ever tried to do the two tasks at the same time? I mean, you do the editing mask prediction, you also do the classification prediction.
Yeah. In the actually, this is a data set. This work will only propose the data set, so we do not propose our own method. So we just tested some existing method here. Okay.
Okay, so they only conduct one task or okay. Some results show the mask result. Some methods do not show, right? If the method show both classification result and the segmentation results, which means they do the two or three tasks at the same time, right?
Yes, right.
Okay, I see. Uh, okay, I see. Okay, good. So maybe we also back to the ready work, and I also have a question. So how many synthesized data do you use? I mean, uh, how many images in the virtual source data set?
We just use the person X. And during the third module, the sampling module, there may be more. There may be some images can be sampled for multiple times. So
Okay.
yeah.
So okay, so maybe my main question is whether we could use more data, and if we involve more data, and the general performance will also be better. Yeah.
I think so. Yeah.
Yeah. So yeah, maybe it is due to uh the the number of images which is not enough. I mean, if we have the sufficient data and yeah, I think it can be better. Yes.
Yeah, right. So as I listed, there are many virtual virtual images, but a virtual data set. But now we just use person X for our experiments. So I think if we include more data set, the performance will be enhanced. Yeah.
Yeah. The way person is from the Yimang, right? I remember it's by the
Yeah.
group of Yimang. And yeah, I just have one question. Have you ever tried his data set? I think it's generated by the GAN, the GTA 5, and to generate the way person. But I never try it. So have you ever tried it at all? Yeah.
No,
Okay.
no, I haven't tried.
Uh, okay, I see. I think it is more close to the real world because it has more patterns on the clothes have more color changes and more weather changes, right?
Yeah.
So I also not try it, but I think it can be, maybe it can be better, but
Yeah.
I'm not sure. Yeah. So do you any question from our audience? You can raise your hands or yeah, or type your question in the chat box, and we have a chat room, and you can send your question in the chat room. Yeah. So okay. So I see. So okay, maybe I ask one more question about the second work.
Oh,
Actually, I have
all
seen
right.
many works on the I mean the fake detection, right? I see many works, but they have different benchmarks. I mean, some method using one benchmark, some method use another benchmarks, but the question is they do not using the same editing. I mean, they do not use the same deep fake, so the data set is different. So usually we cannot say which method is work better because it can specify on the data set. It can be overfit on certain editing. So could you ensure, I mean, how to find a better way to robust to different kinds of editing? The method is scalable to different editing. So do you have any insights on this problem?
Um, I just think maybe if the method can train down more data with more acting method, it can be more generative. It it can be more general. And in this work, there are three image editing methods are used in the dataset, including including face swapping, inputting, and attribute editing. And in previous works, there are only face swapping and attribute editing. And in this dataset, we also propose the inputting task. So I think with when the model can detect the inputting, it can be more general. So because in previous methods, the attribute editing are always focused on edit the specific regions like the person's eye or the person's nose, the lips. So the inputting tasks are more, I think it's more general because it can input in any region of the image.
Okay, I see. So in painting, you also do the, most time we do the editing on the face area. So you mean the in painting also do the on no face area, right?
Yeah, right.
Okay, so yeah, but I have one more question. Maybe in our real life, the women will do the physical changes like the makeup. So whether you think the makeup should be detected or not, like the 化妆, right? Makeup should be detected or not detected by the fake detection.
I think not. If the makeup is, I don't know what it means. The makeup is by the person itself or by the generative model.
Okay, but sometimes it is same for the computer, right? The computer see you make up, but he,
Yeah, but
yeah,
they might be in different patterns.
yeah.
The
But
people
how
make
about the real makeup? The person do it by himself, and yeah, whether we should detect whether he is makeup or not, is it kind of the fake detection should be detected?
No, I think this
Okay.
shouldn't be detected because there are many people they have makeup, but it is real. image. It is not a fake image, I think.
Okay. So
Okay.
yeah. Maybe I will still have maybe 5 minutes. So how about the people if go to the South Korea and they change their face, maybe to do some face modification? Is it
Yeah.
to be detected?
Well, I think not, because as I just mentioned, uh, it is even when people have modification in their own face or they have their own makeups, but in the image, this is still the real image. The image is not edited. Yeah. So when the image is not edited by computer, it should not be um, viewed as a fake image. Yeah.
Yeah. Actually, I have talked with our some professors at Macau, and they usually do it in a signal level.
Oh,
They analyze the image into different signals and see whether the signal is changed. So if the signal is changed, it can be editing, right?
interesting. Yeah, right.
Right.
Yeah,
Okay,
right.
good. So thanks for Professor Lin, and we will have 10 minutes uh break, and we will come back at the I think 10:30. We will come back at 10:30. And thanks for Professor Lin, and we have a break.
Okay, thank you.
Okay.
We just finished. Yeah, 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 that's right. So can you take a picture?
Okay, could you see my screen about the schedule? Okay, screen share is loading. Why? Uh, yes, you may stop the sharing and I will share the schedule. Yeah,
Oh.
good. Sure. Right. Zhihe, could you share the screen? Okay, I will stop sharing and then let you share.
Oh, sure.
Okay,
Yeah,
thanks.
can you hear me?
Yeah,
Oh,
I
sure.
can hear you. Yeah.
Okay.
Um,
So now you can see my screen, right?
yes, it
Okay.
is. It's good.
Yeah, we can screen, yes.
Okay, perfect.
Okay, good. So, Dr. Zhihe is graduate from the University of Surrey, under the supervision of Professor Xiang Tao and Professor Song Yizhe. And currently, the Zhihe is the postdoc at the the NUS, University of Singapore, working closely with the Professor Wang Xingchao. So let's welcome the Zhihe to give a talk on the future learning from the meta learning to efficient tuning. Right. Thanks, Zhihe.
Thank you for the introduction, Zhedong. Thank you for inviting me to this conference and give this presentation. I also want to, this is a special day. I want to, say happy Dragon Boat Festival to all 端午节安康 to all the people who actually celebrate this festival. Okay, without further ado, I'll start my presentation. So the topic of my presentation is fixed learning from meta learning to efficient tuning. So from the first side, the fixed learning I give the topic is seems irrelevant to the personality, but it's actually not. So for fixed learning, it's a general technical that can be applied into different domains. Like we can also do fixed learning for personality, right? So next, for my presentation. My presentation has several parts. First is background. Second one, I'll introduce meta-learning based fixed learning methods. And the third is the efficient tuning based fixed learning methods and some future works. So first, I'll show some background. So why is fixed learning needed? So there are two main reasons. The first one is that we want to reduce the reliance of deep models on large-scale data sets. Because building such large-scale data sets is labor cost and time-consuming. For example, the popular ImageNet data set was first proposed in 2009 with 3 years building it. It's a lot of effort to annotating such a big data set. So one question just raised. So can we train or adapt a model with limited supervision? For example, fixed examples. The second reason is that we want a model to have the ability like human beings. So that is to learn from a few shot labeled examples. Let me illustrate this process. So there is one photo of dog, and here is a kid. So when the kid saw this dog, we call this is learning process, just one photo of dog. So after learning, actually this kid can recognize all types of dogs in our real life. So we want the model to have the similar ability like this. So after introducing the background, let's come to the meta-learning based few-shot learning. Before introducing the meta-learning based pipeline, I'll introduce the supervised learning to better understand the difference between them. So for the supervised learning, I would say in these tasks, the image and the class are binding. So why? How? As we have two classes, one dog and one otter, and there are many classes under each class. So we use these images to train the model, and then this model can actually do the binary classification, especially during inference when there is a new image for dog, the model can recognize this image as a dog. And for meta-learning based methods, the data here is not image, it's actually task. And in each task, the image and the class are not binding. How? So in this task one, we have two classes, one flowers and one bags. And under each class, we have several images. So actually the model is trained to recognize the given query image to one of the classes. Similarly for the task two. So the model also wants to classify this given query image into two given classes in the suppose set. So during inference, the model can recognize the given query image based on the information of the suppose set. So the suppose set here is the n-way k-shot. That means here in the example, we have two way, and in each way, we have 4 shots. So it's actually the two-way 4-shot learning. So this is the difference between the few-shot learning and the traditional supervised learning. So I'll show more examples to how the image and the class are not binding in few-shot learning. So in this task one, we see the dog is the class 1 and the flower is the class 2. And in the task 2, actually the flower is class 1 and the otter is the class 2. So the image and the class are not binding. So all the classes in one task will be reordered and renamed into different classes. And due to the technical aspects, we can actually divide the meta-learning based method into 3 categories. The first one is based on similarity. The second one is based on the learning algorithm. Third one is based on data. So let's see. This is the category actually depends on how the methods leverage the prior knowledge. So first type, so the prior knowledge about similarity. In this category, the methods want to learn the embeddings to discriminate 2 or more unseen classes. I show some representative methods under each category. And for the second category, so this category want to design a method to better learn the model. So after learning, this model can be easily adapted on a smarter set to give good results on a new task. And for the third category is they leverage the prior knowledge about the data. So this is pretty simple and easy to understand. That is, as we only have the n-way k-shot data set, support set to train the model or adapt the model. So in the third type, they actually want to leverage some generative models to generate more images for each class. So then we have more images to train the model. So it can train a more generalizable model. So next, I'll introduce some works under the first and the second categories. So first category based on similarity. The first work I want to introduce is the matching network, which was published on NeurIPS 2016. So in this method, they actually they have two encoders to embed the support images and the query image into the feature embeddings. And after embedding, so these features, the query features will be used to compute the similarity with the support features to get the similarity score. And this score will be used as the weights for the labels of the support set. And then this weighted label, we sum this weighted label as the new predictable label for the query image. So this is how they do during training. The second one is a prototypical neural network, so which was published on NeurIPS 2017. So in this work, they actually want to learn a very powerful model to embed the images. So after learning the model, as we have n-way k-shot images, we can input these images into the pre-trained model, and this model can, with this model, we can get for each class we have k embeddings because we have a k-shot, right? We have k embeddings, and these k embeddings will compute the mean of these k embeddings. We regard this mean as the prototype. So this prototype actually can represent this particular class. And we do the similar thing for different class. We have actually here in this figure, we have three prototypes. And when there is one query image comes, we can just compute the similarity between the query image feature and the prototype. And then the distance actually can determine which class this query image belongs to. The next work I want to introduce is the relation network. I show the comparison among these three methods. So like the matching network during the similarity computation, they actually use all the images from different classes in the support set. And for the prototypical network, they actually first to compute the prototype from each class, and then use the query feature to compute the Euclidean distance with the each support prototype. And for the relation network, so it is to advance the prototypical network. So they don't use the Euclidean distance. In this work, they actually design a learnable module called the relation module. So this relation module is actually to replace the Euclidean distance to compute the similarity. And next, I'll introduce two works under the learning categories. So the first work is a very popular one called Memo, which was published on ICMR 2017. It has been cited by 12K so far. It's a big achievement in our field. And in this Memo method, there are two steps. So the first one is task learning. The second one is meta learning. So how they do this? So first, during training, we have the pre-trained model, we can get the global parameter, right? And with this global parameter, we can further update it, use the gradient descent on a particular task. We call this task 1. So then we can do the similar thing for task 2 and for task 3. So we get the phi 1, phi 2, phi 3 for different tasks. And the second step is the meta-learning. So actually, we want to learn a generalized model, and this model should work on diverse tasks. So intuitively, we can actually compute the second order gradient descent with the parameters computed on each task. So this is the sum of the loss function on all tasks. So after this step of gradient descent, actually this model can work well on different tasks. It is more generalizable. And the Reptile, this work, which was published on arXiv 2018. So this work is, they adopt a different training pipeline. So in this work, they also have the global parameters, right? And with this global parameter, they'll first compute the parameters on a particular task. We call this task J. And then the parameter of task J will be used to update the global parameter in with this formulation. Also do the gradient descent. So, and then the second one on task 2, they do the similar thing. So different from the memo, they first compute the parameters from different tasks and then do the sum to minimize the loss function. Actually, Reptile actually do this process step by step. Although the meta-learning based methods are impressive on learning with few shot examples, the limitations of these methods are still obvious. That is, so these methods often meta-learn a pre-trained model with many tasks. So, building such many tasks is still time-consuming process. And secondly, after meta-training, this model can adapt on n-way K-shot samples and can only work for n-way classification only. So actually, the n-way here is a small number. So usually it's a 5-way, 10-way. So it's not enough in real application. So for the first limitation, actually we can leverage the pre-trained foundation models, as they are also the pre-trained models, but they are more powerful. We don't need many tasks to further meta-learn it. And then secondly, we can do the efficient tuning of the pre-trained foundation models. And then after efficient tuning, this model can actually work for dataset-wise classification. So then let's come to the efficient tuning-based methods. Before introducing the particular methods, I'll give some background. So the foundation models we focused here is the CLIP. So it's from the paper Learning Transferable Visual Models from Natural Language Supervision, which was published on ICMR 2021. Just for 3 years, it has been cited by 16K times. So it's a very big achievement. So for CLIP model, in this paper, they collect 400 million image text pairs. And for the model, they have 2 encoders. So for these 2 encoders are used to embed different modalities. For the text encoder, they embed the text descriptions into the text embeddings. And the image encoder is to embed the images to the image features. So the objective of the CLIP model is actually to force the paired image text to be close to each other in the common space, and to force the unpaired image text pairs to be away from each other. So after the contrastive pre-training, this model can be used for classification in a zero-shot manner. How they can do this? So that is as we have, if we want to classify n classes, we just need the name of these classes, like here, the playing car, dog, and bird. And with this class name, we have a template, a photo of a. So a photo of a combined with this class name as the language description. We input this class-wise language description into the text encoder. We can get the class embeddings. And these class embeddings can be used as the classifier. How? So, for example, when there is a query image, we input it into the image encoder, we get the image feature. And this image feature will be used to compute the cosine similarity with the class embeddings. So then we can get the highest similarity score on a particular class. So that means this query image belongs to that class. So this is how it works. So how to efficiently tune the clean model? There are two main pipelines. The first one is prop tuning. So in this work, they actually assume that the generic template, a photo of a, is not suitable for all tasks. So in this work, they introduce some learnable prompt. They call the learnable context in front of the, to replace the a photo of a, and they tune this learnable context with a fixed shot dataset. And then after tuning, this model can this model can work better on a particular task. The second tuning pipeline is called adapter style tuning. So instead of adding some learnable parameters in front of the clip model, they actually add some learnable layers at the end of the model. And these layers will be used to update the pre-trained features to a new one. And then these new features will be used to compute the similarity to get the final score. So after introducing some background, I'll introduce some of my works. The first one called the task residual for tuning vision language models, which was published on ICMR 2023. So I show the comparison among different methods in this figure. The first A is the zero-shot clip. The second one is prop tuning, as I mentioned. So in this prop tuning, they add some parameters in front of the text encoder, and then this texture prompts will go through the texture encoder and do backward in each iteration. So it hugely increased the training time. In contrast, the adapter style tuning doesn't have this problem, but it has its own problem. That is, it's too biased to the pre-trained features. That is because the input of the adapter is the pre-trained features. So the output is too dependent on the input features. In this way, it lacks the flexibility to explore the task-specific knowledge. So in our work, we propose a very simple yet effective solution for this. So we actually introduce a set of independent parameters. We call it task residual. Note that this task residual is totally independent from the pre-trained features or pre-trained parameters. So they can better explore the task-specific knowledge. And as we add some parameters at the end of the text encoder, we only run the text encoder just once. So it is also training efficient. So overall, our method actually have two advantages. First, it is training efficient. Secondly, it is more flexible to explore the task-specific knowledge. And let's see some results. The left figure shows the correlation between the number of tunable parameters and the performance accuracy. So we conduct the evaluation under different shots on ImageNet. We can see that our method can always achieve a higher performance with less tunable parameters. In the right figure, we show the average performance over 11 recognition datasets. These recognition tasks include generic object recognition, fine-grained object recognition, scene recognition, textual recognition, imagery, satellite imagery recognition, and also action recognition, right? And we can see our method can always achieve a new SOTA performance on the average performance of 11 datasets. Let me summarize this work. So in this work, we first observed the limitations of existing methods. And based on that, we actually propose a new tuning paradigm called task residual tuning. Secondly, our method is more parameter efficient and easy to implement. Theoretically, we can only use one line of code to implement our method. So thirdly, we verify the effectiveness of our method on 11 recognition tasks to show its performance. The second work is graph adapter, tuning vision language models with dual knowledge graph, which was published on New York 2023. So in this work, we assume that there are some structural knowledge stored in the pre-trained models, but previous methods do not explore this type of knowledge. So in this work, we for the first time to leverage this type of knowledge by using graph adapter. So from the figure, we can see the obvious comparison that our method is the first to leverage the structure knowledge. How it works, let's see the details. So in this graph adapter, we actually designed two subgraphs, and these subgraphs are used for different modalities. I'll take the texture subgraph as an example to show how it works. So during training, although first, before training, we have the texture descriptions. We input these texture descriptions into the text encoder, we get the texture embeddings. And as we have K classes, we have K by D metric for the texture embeddings. And with these texture embeddings, we can actually build the subgraph with K nodes. It's the initial subgraph. And during training, when there is a textual description comes, we can input it into the text encoder. We get a texture embedding. This embedding will be used to insert into the initial subgraph to get a new subgraph by updating. So this new subgraph actually has K+1 nodes. And after updating, we extract these updated nodes. Similarly, we can get another updated embedding from the visual subgraph. And these two embeddings will be used to do the reweighting to get a new texture embedding. This texture embedding will be used to compute the similarity with the image features to do the final prediction. This is the whole process. As we also evaluate our method on 11 recognition datasets, as I mentioned before. And as you can see, under 1, 2, 4, 8, and 16 shots, our method can continuously advance other methods. And it is, you can see the performance gap is really large. Let me summarize this work. So in this work, we, for the first time, to explore the structural knowledge from the pre-trained vision language models for efficient tuning. So secondly, we propose a dual knowledge graph called a graph adapter to model the structural knowledge from two modalities. Thirdly, we evaluate our method on diverse benchmarks to show its state-of-the-art performance. Next, I'll introduce some future works actually two future works. The first one, as we have some pre-trained foundation models, these models are so powerful and generalizable. For the previous efficient tuning, we still need some official data set to efficient tune the model. So I want to ask, so can we just use these pre-trained models in a zero-shot manner and also boost these models in a zero-shot learning manner? So this is promising. Actually, we have done one work to leverage the train of thought to enhance the zero-shot performance of clip. And another type of zero-shot learning to boost the performance is that they can actually use the prompt engineering to boost the performance of zero-shot clip. Second promising direction is that as we have multiple models, so we actually can leverage these models to work together for a more generable performance, right? So we can actually get some inspiration from the ensemble learning methods or the mixture of experts, this type of technicals or methods to actually design some particular methods to leverage some pre-trained foundation models. So actually, we just finished one work. So beyond strengths, customized ensembles for generalized vision language models, which was published on ICMR 2024. Actually, in this work, we explore three ensemble learning strategies for three particular scenarios. So I think that's all for my presentation. I still have 1 minute, I think. So should we do a Q&A or?
Yeah. Thanks, Zhihe. Maybe we could ask more questions because when later talk is cancelled, so we could talk a little bit. Yeah. So
Okay.
thanks a lot, Zhihe. And actually, I have two questions. For the first work, I'm just interested in the difference from the COOP. So the task prompt is learnable or not? So yeah. Here I just confused what's the main difference from the B and the D. I think they are quite similar because they are all learnable, right?
They're all learnable, correct. The difference is that actually, as I mentioned, the prompt tuning, or you call it, is from the hoop method, right? Actually, this method, they add the parameters in front of the text encoder. So that means although the text encoder is frozen, totally frozen during training. So the prompt, I would say the learnable prompt will go through the text embedding and do the backward each time because it is needed to be updated. So it is not training efficient. So we actually we do not we want to use the text encoder just once, and this to make it be training efficient, and we add the parameter at the end of the model. So
I see. So I know every time if we want to backward the gradient, it will need to store the gradients. So the prompt tuning costs more memory on GPU, right? But
yeah, that's right.
But your method is adding the parameters at the end of the text encoder, right? So it costs less. Sorry, I have another question. Is the task residue is it learnable? It is same for every prompt, right? It is learnable, but it is when we do the inference, it is fixed.
It is fixed.
Okay. Okay, I see. Have you ever compare? So sorry, I do not work in this field, but I see a lot of work from the Kaiyang. Actually, I think Kaiyang is also work. So have you ever compared your work with the Kaiyang? Yeah.
Yeah, sure. Actually, the prompt tuning is from Kaiyang. Kaiyang is my senior fellow. We have the same supervisor. Yeah.
Okay.
Yeah. Actually, Kaiyang do two wonderful works. One is called Coop and the other called Co-Coop. So and one for feature learning, one for base tuning generalization.
Yeah. So, have you ever compared with him or ICCOP and
Yeah, actually, so this Coop is actually here because this their method. So Kayan's method is very early. It's the pioneer work. So the performance of the work is not sort of anymore. So yeah, it's kind
I
of
think he also have a Coop plus plus or Coop Coop. I forgot.
Co-Coop. Actually, Co-Coop is not for the similar scenario. Co-Coop is just is for generalization. So they actually want to learn the model or efficient tune the model on base classes, and then they directly use the model from some novel classes. So this is different scenario.
Okay, I see. Okay, good. So the second work you using graphic neural network, right?
Yeah.
I think it's quite so how about the graph? The graph is it's a perfect graph or you build it like the KNN or how to build the graph? I mean
Actually, we have the after we input the language descriptions into the text encoder, we have the textual embeddings.
Yeah.
So as we have K classes, and each embedding actually has D dimension, and this is a K by D matrix. We can use this textual embedding to build the subgraph, and we have K nodes for K classes, and we compute the similarity between each class or interclass similarity as the edge.
Okay, so it is fully connected, right, between every nodes.
Yeah, sure.
Okay, I see. So, I think the main idea is quite close to the, like the query expansion. We have the middle string like the query and the query to find the most similar other galleries and to do the query expansion. Do you think it is quite close or?
I'll say they are. I'll say they actually start from different perspectives. Our work actually want to leverage the knowledge from the pre-trained vision language models. For that work, maybe there are some technical similarity, but from motivation or other perspective, they are different.
Yeah. But sorry. I think it can be also can be done by transformer.
Yeah, sure.
Yeah.
Yeah, actually, transformer is a specific graph modality or graph structure.
Yeah, sure.
Yeah.
Okay, thank you. Do any audience have question? You can raise your hands or just unmute your microphone to ask some question. Yeah.
Yeah, okay. Thank you, Joe. I also have one question about the paradigm of zero-shot clip. Okay, can you hear me?
This one, you mean the future work?
Yeah, the first one to work. For scene we've never seen before, so probably we don't know the name. It's category name. So in this case, how do we perform zero-shot clip?
Oh, you don't know the category name. So this is hard for the clip. So clip need at least they just need the names of class. They don't need the images. So I think the name of class is essential.
Okay.
Yeah, and for zero-shot learning, actually, I would say the first type of zero-shot learning is the prompt engineering. So as I mentioned here, so for the zero-shot clip, they actually used a photo of as the template. And before, there are many researchers actually want to design different templates for different type of data size. So that one can actually boost the zero-shot performance of clip. And for example, so if you have a data set for tests, so you can use a template, a photo of a class and a comma with a photo of a type of pet. So just with this additional words, a type of pet, the performance can be improved by 2% from that paper.
Okay, so this text embeddings, they act just like the classifier. So in this paradigm, you mean the category names are necessary, right?
Yeah. Because they train in this way. They want to you build the connection between the image and the text.
Okay, thank you.
Thank you.
Any question from the live audience? Okay.
Okay, good.
Oh, yeah.
So
Thank you.
thanks for the Zhihe's talk, and it's really, really great. And next we will go through our workshop papers. Actually, we have 3 workshop papers, which is selected as oral presentation. But one author is missing because he attended a competition. So anyway, let's welcome our first speaker from the Xiamen University, Dai Li Cun. Actually, could you share your screen? Yeah.
Hello. Can you hear me?
Yeah, we can hear you.
Okay.
Good.
Okay. Is it clear?
Yes. Let's begin.
Okay. Hello, everyone. I'm Li Dai. I'm glad to introduce our recent work exploring part features for unsupervised visible infrared person identification. The work is about VI-RealID, which targets at matching visible or infrared images of the same person from another modality. It is crucial in the society security system. Unlike traditional person RealID, which suffers from intra-modality discrepancy, VI-RealID is more challenging because of the large modality gap between visible and infrared images. Existing VI-RealID methods can be roughly categorized into image level and feature level methods. The image level methods generate cross-modality images and extract modality invariant features from aligned images. In contrast, feature level methods focus on finding a modality shared feature space or constructing a modality specific feature space to minimize the discrepancy. Although existing VI-RealID methods have achieved promising performance recently, but are difficult to apply in practice because they rely on trusted labels of the dataset, which are time-consuming and labor-intensive. Therefore, it is important to achieve an efficient VI-RealID model without annotations, which is called unsupervised VI-RealID. Recent unsupervised VI-RealID methods focus on building accurate cross-modality relationships with clustering and matching algorithms. However, these methods are designed with a global vision, which leaves the fine-grained part features unexplored, resulting in insufficient learning. Therefore, we investigate part features for unsupervised VI-RealID in this work. In our solution, we propose a part-based cross-modality learning framework. In this framework, we design part-integrated dual contrastive learning to introduce part features. Then, a part-assisted multiple matching module is introduced to match clusters from 2 modalities in the bipartial graph matching process. Finally, a cross-alignment learning module is devised to align features from 3 perspectives. The training of the model alternates between label generation and model learning. Our framework starts from the part-integrated dual-contrastive learning module, which introduces part features for discriminative feature learning. We first extract the feature map of the image and obtain the global feature by applying global average pooling over the feature map. Then, a clustering algorithm is employed to assign pursuit labels to each sample and construct memory banks for each modality. Additionally, we obtain part features of a sample by dividing the feature map into several regions and applying regional pooling. For global feature, we conduct contrastive learning with the memory banks. The part features share the pursuit labels of the global features, and the contrastive learning is conducted with their memory banks as well. Meanwhile, to learn discriminative part features, we introduce a part diversity loss for part features, which forces the model to focus on different parts of images. To associate samples from different modalities, we propose a multiple matching algorithm by defining the cluster matching problem as a bipartial graph problem. The nodes are represented by clusters, and the weight between two nodes is defined as the dissimilarity of clusters. Additionally, to exploit fine-grained information to associate clusters, we introduce part features to assist in the definition of similarity between nodes with a weighted strategy, which considers the probability prediction of a part feature belonging to the cluster according to its memory bank. The graph matching formulation can be solved by Hungarian algorithm. However, the number of clusters into modalities is often unbalanced due to the modality gap. So we assume that visible clusters are more than infrared clusters, and then we duplicate infrared nodes several times to allow different visible clusters to match the same infrared cluster. After that, we perform the first round of matching. Then, we select visible clusters that match infrared clusters with the same identity, and those infrared clusters that are not matched by any clusters or matched by several clusters to perform the second round matching, since they tend to have ambiguous matching. Finally, we modify the relationship of clusters and merge the visible clusters that match the same cluster. To conduct cross-modality learning, we construct two modality-specific memory banks and a modality shared memory bank initialized by cluster centroids from two modalities for both global and as well as part features. To reduce the effects of incorrect labels, we devise cross-alignment learning to align diverse features from three perspectives: global with part, modality-specific with modality shared, and visible with infrared. For global with part, we align the prediction of global features with part features from their modality shared memories by KL divergence, since they should be consistent with different memory banks. Additionally, we also align the part features batch level self-similarity to global features. Similarly, for modality specific with modality shared, we align the predictions of features with modality specific and modality shared memory banks to constrain the consistency of different representations of identity. For part features, we align its prediction of modality-specific memory to its global features. Meanwhile, a modality classifier is applied to align visible and infrared features. The overall training loss function is summarized as contrastive linear loss, alignment loss, and part diversity loss. The training of our framework contains two stages. The first stage conducts PDC learning, and the second performs cross-modality learning with our part-based cross-modality learning framework. Our method is evaluated on two public visible infrared datasets. We adopt rank 1, mean average precision, and mean inverse negative penalty under four-test mode for comparison. It can be seen that the MAP of our method surpasses state-of-the-art method, while our method employs a smaller batch size and does not require any additional labeled person re-ID dataset for pre-training the model. We also conduct ambulation studies on the REGDB dataset to further prove the effectiveness of each component in our framework. The baseline indicates the PDC learning framework. The results show improvement brought by each model in our framework. The baseline obtains discriminative information with global and part features, but cannot effectively reduce the modality gap. The MM and the PMM can effectively construct a cross-modality relationship for heterogeneous learning. The CAL aligns features and further improves performance. In conclusion, in this work, we introduce a part-integrated cross-modality learning framework for unsupervised VRID. We propose a part-assisted multiple matching module to match clusters by weighted bipartial graph matching. A cross-alignment learning module is proposed to encourage discriminative feature extraction. In our future work, we are going to explore better part feature generation and the usage of part features in other unsupervised cross-modality scanners. For more information, please refer to our paper or reach me through the email. Thank you for your attention.
Yeah, thanks, Li Chun. And any person have any question? Yeah. Okay. Okay, good. So thanks, Li Chun, for the talk, and we will have our next oral presentation by Junqi. Yeah, thanks, Li Chun. Junqi, could you share the screen?
Okay, can you hear me?
Yeah, I can hear you.
Can you hear can you see my screen?
Yeah, I can see your I can see your
Okay.
screen right now. You may try to play the slides.
Okay. Hello everyone. My name is Lu Junqi. I came from the University of Macau. Today I'm glad to show my work analytical study of DreamGaussian and MTN in the field of 3D generation. It's mainly for 3D generative field comprehensive show and some thinking. The one of the AIGC marks the pivotal epoch in technological evolution, fueled by advancement in deep learning algorithms and big data. The revolution has pushed the boundary of the creative potential. Notable examples include the OpenAI's GPT-4 and GPT-Fusion, which is generating vivid images from the prompts. Fundamental AIGC relies on pre-trained generative models. For instance, the prompt photograph ocean reading a horse. Feeding this into AIGC system it will generate beautiful images or a 3D model. The process mirrors forms the guide creativities, which output that aligns the people's expectation. The Royal 3D content generator had witnessed a potential growth fueled by innovations that bridge the gap between the digital and tangible world. The domain is incompetent image 3D, text 3D, and image plus text to 3D. Each is pushing the frontiers, statistics, methodologies, and expanding the horizons, the creativity and utility. There's many outstanding methods in the field of 3D generation. This is such as NERF's ghost landing, dream fusion, instant 3D, 3D GANs, and so on. This guided by the 3D gen method, we can project the data representations from 3D models that can be applied, such as a point cloud, mesh volumetric, and project with RGBD. My paper centers the demonstrated study comparing two 3D generation method, DreamGaussian, which innovatively applied generative Gaussian blending for enhanced 3D output, and multi-scale triple-line network, a sophisticated text to 3D approach utilizing the multi-scale line for improved semantic occurrence in the model generation. Through the extensive analysis, the researchers evaluated their distinct contribution and efficiency in advanced 3D data creation. The first stage is DreamGaussian. DreamGaussian is a novel 3D context creation framework that significantly reduces generation times by applying Gaussian distribution. It includes three main steps. The first step is generative 3D Gaussian blending. It is uses 3D Gaussian blending for coarse 3D representation. This method leverages the single well distillation sampling to optimize the initial geometry and appearance efficiently. The next step is efficient mesh extraction. After generating the 3D Gaussian distribution, an effector algorithm is extracted to extract the texture polygon mesh. It requires local density contrast dense measure using marching cubic technique and smooth the mesh enhance quality. The final is the UV special texture refinement. Introduce the refinement stage to address initial texture fusion. This stage uses image space supervisation to fine-tune the text details on the grid, enhance its clarity. This process reflects balance optimization types and generation quality. It's both image to 3D and text to 3D talks, resulting in the detailed 3D math and 3D videos. In the right column, actually training progress, DreamGaussian will real the image to remove the background to train the models to interpret. The Y is the Gaussian blending stage, and another is a mesh training stage. The 3D model will iteratively optimize from a sphere slowly to generate the target shape. The second is MT. Multi-scale triple line network is also a innovative method for generating 3D objects from natural language. This model learns four stages, progressing from low to high resolution, with vectors representing images and stage features using a Fusion Stable Diffusion model. It calls the SDS loss score by inputting a noise RGBD image, timestamp, and prompts. There are three components involved in the generating RGB image. In this middle, the first is frontier transform. This is enhanced learning is a high frequency function by transforming the effect vector into stationary kernel with a tunable bandwidth. The next is a triple decoder. It uses a multi-layer precision to estimate color and density, leverage the frontier features for improved performance. The final is volume rendering. It projects 3D features into the RGB image, which is used to input for the stable diffusion model and compute the loss score. By combining these components, MT effectively transforms text description into detailed 3D models, significantly reducing the efforts required for a manual 3D modeling and providing a more intuitive way to create 3D content. This section it shows the 3D generated results for text 3D charts, comparing outputs of DreamGaussian and MTA using the same prompts. As illustrated in the image, the DreamGaussian method is based on 0, 1, 2, 3 model. Produce 3D models with many patch and rough surface. In contrast, the MT method generates models with more uniform colors and smaller surface, but it is significantly slower than the DreamGaussian. This board represents the comparative analysis of DreamGaussian image to 3D based stable 0, 1, 3 and the image plus text to 3D based on image stream. This column shows the input images, and the left column it shows text prompt used for the image text plus text to 3D generation. Below the generated 3D models, these numbers represent the elevation of the clip similarities, indicating a degraded similarity between the generated 3D and the original image. The front wheel of the generated 3D is clear, but the back wheel is less accurate. The final geometric details are not well rendered. However, in these terms, both of the visual quality and the label similarity, the image to 3D method perform better. Despite this, DreamGaussian still have significant room for improved in 3D modeling scenario. In conclusion, in the futures, the advancement in the 3D generations will focus on the improving accuracy of the generated geometry construction, enhancing the detailed recovery capabilities, and increasing efficiency in the handling large-scale models. Additionally, there will be efforts to refine evolution method for assessing model quality, enhancing semantic understanding for more textual relevant outputs. The integrated multi-models improves for comprehensive model synthetics. Useless, this advancement aims to produce for more realistic and detailed 3D models across various applications. That's all. Thanks for watching.
Okay, thanks for Junqi to sharing the 3D reconstruction. And actually, our objective idea is to do the multi-view retrieval, multi-view recognize, multi-view matching. So we think the 3D modeling is also within our scope. So this time we also invite ThingWorks on 3D to our workshop and to do the sharing. Yeah, all good. So any question? Okay, good. So this is all for our workshop, and yeah, thanks for all to attend our workshop, and have a nice day. And this is the end of our workshop, and we will record the workshop and upload it to YouTube and several video website. And later I will share the link on our website, and you can check and to see the presentation. Yeah, thanks for all, and I will stop recording and stop the Zoom recording.